All right.
What are bell ringers?
Great question. Bell ringers are usually like questions on previously learned material. So when you come in and the bell rings, you should be in your seat, right?
Yeah.
You would answer the question. Just in your notes or something. But today I just reviewed, right? We just auditorily reviewed. I didn't have you. Essentially, I just asked you multiple bell ringers instead of having it on the board. Okay. All right. Darn it, that's what I forgot.
I didn't get it.
You didn't get it?
Okay.
I knew I forgot something. I'll be right back.
Perfect. So she just come back to the house before. That's not bad. Oh, it's lunch after this.
Carly, this Friday.
Ooh, that sounds
Every
good.
Friday. Yellow pizza. Yellow.
Oh, are you guys going to watch the game today?
Going to the football game?
Yeah.
Yeah.
Okay. While I get some stuff set up, why don't you at least start getting this in?
That's quite. Well, I didn't say it. All right, so really what this is just saying is really about just about science in general, that really what's really important to science is having good models. So why is that important, and what is a model? What can models be? Beautiful girls.
Daniel! Don't let me touch that. I've touched that and burned myself so many times thinking it wasn't hot. I suppose you could say that, but all girls are beautiful, Daniel. I think so.
Some on the inside, some on the outside.
All of them. No. All right. What was I going to say? So models. Models are very, very important to science because, just think about it. Chemistry, we're dealing with atoms. Why do you think a model would be important in chemistry?
Models are larger than actual atoms.
Yeah, I mean, so there's all kinds of models. Did you guys know that a math equation is a model? It models some real life thing. It's not just some make-believe. So whenever you say, when am I going to use this? Well, believe it or not, every math equation is a model of some real life situation. I had a student a couple years ago, and he wasn't a very good student. I don't mean that he wasn't smart. I mean he just didn't try or do any work or care at all. And you remember him coming back and he goes, "Man, I wish I would have paid attention to geometry. I use it every day at work." You know, he messed around.
What work did he do?
He did some sort of like, I don't know, it was like putting in furnaces and doing HVAC stuff.
I don't know. It's quite
You're not gonna do it if it requires geometry, is that what you said? Okay.
I'll check.
Because the point is, models, most of the models we think of are like visual, right? Like, you know, a model of an atom would be, yes, it is bigger to scale, and we need it to, because we can't see an atom, right? But a model is a simplification of a complex process or idea. Remember here what I said, a model, maybe you want to write this down. A model is a simplification of a complex, what did I say?
A model is a simplification of a complex idea.
Complex, so a model is a simplification of a complex idea.
No,
Complex
Thing.
thing, yeah, substance, yeah, complex. Again, I'm just making this up. I mean, there's an actual definition. This is like a like a simplified definition. So a model is just taking some complex reality and simplifying it. Yeah, very complex, right?
Why do I feel that every single math equation is harder?
Because if we really did it without the math equation, it'd be really hard. Okay. All right, so kinetic molecular theory, we're gonna spend some time talking about this. The kinetic molecular theory is that all these tiny particles that we said exist in the non-continuous particle theory of matter, got all these little tiny atoms, they do stuff.
What you said?
I didn't think it was that funny, Daniel. Are you tired, Daniel? Do you need some sleep?
If I need some sleep, I'll just sleep right now.
That's true. That's the important kicker here that we're trying to emphasize now. Is this hard to wrap our minds around, or do we feel like this is something that's pretty straightforward?
I get it.
Why do you get it? What tells you that this is true?
Because the teacher said so.
That's not a good answer.
Because it makes sense.
Why? What in reality would help you for this to make sense? Is this desk moving?
Yes, it is.
So,
It's vibrating right now.
It is moving. Yes, it is vibrating.
I'm so good at this all the time.
Right now, your desk, I mean, your chair is vibrating your booty.
Yeah, so that you won't go through it.
Okay, at a subatomic level, all solids are moving. They're vibrating, but we just can't see it. Liquids, when you put a liquid in a glass and you let it settle, it doesn't look like it's moving, is it?
But it is
But it's moving.
vibrating.
The ones that we can usually see a little bit better are the gases as far as their ability to move. But can we see this gas move?
No, we cannot.
Well, right now, you guys are getting pelted in the face with particle after particle after particle. I'm serious. This is partly why when you guys go up in an airplane, what happens? Your ears pop. And the reason why is because when you go up in the atmosphere, okay, you have less air pressure, less particles above you. And so you've got an equilibrium in your body. You got pressure pushing out from inside your body and air particles hitting you in the face, exerting a pressure on your body. Those need to be equal. If they're not equal, you feel pressure. You feel a pressure difference. You only notice something if it's, just like I just said earlier, I don't notice it's that cold in here because I'm in here the whole time. But if you go in and out and go in and out, you notice it, right? It's the same idea.
Wait, so our single guy stands in North Pole in this t-shirt, you will not notice it for, if you stayed there for a very long time.
You wouldn't notice it, yeah. For example, so I played basketball in college, and so I would take a lot of ice baths. Does anybody know what that is?
Yes.
Okay.
No.
I would take a lot of ice baths where I would fully submerge myself in a body of water full of ice.
If you just sat in that body of water after a period of time, you wouldn't notice anything. And it wasn't so much that you were numb. What ends up happening is actually your body heat creates this layer, like bubble around you, that like prevents only so much of the cold to be transferred or the heat to be transferred away from you. We used to have these little containers that if you turned on a little motor, it would cycle the water. It would make the water like a whirlpool. That was billions of times worse. Because what it was doing is it was taking and removing all that warm pocket of air that was around you, that was preventing that cold water from making you really, really, really cold, and you just felt infinitely more times worse because of that pocket that was created around you. Okay? So, actually, believe it or not, we have more pressure on us right here from an air standpoint, from air particles above us, stockpiling on us, essentially, is what really it is, than we do when we go up in an airplane. So actually, we have more pressure here than we do in an airplane. Well, why do we notice a difference? Why do our ears pop and hurt? Well, it's not that we have more pressure, it's actually we have less pressure. But the pressure inside our bodies is used to pressure down here. So the pressure inside our bodies are still pushing out like the same pressure on the outside is pushing in. And since it's not balanced anymore, it hurts. Interesting, right? I'm kind of going a little bit over the top of maybe where we should be right now, but
Very interesting.
it's interesting, yes. Okay? Anyways, all that being said, even though you can't see it, everything from a subatomic level is moving. This is what is believed to be true. As soon as particles stop moving, that's when everything ceases. You can't live. Things are dead. So, believe it or not, we can get things cold enough because, maybe you don't know this, but temperature has a lot to do with the motion of a particle, how much energy it has. We can get something so cold that it almost stops, but we can't get it to actually stop. So we can't get it to that theoretically coldest temperature. It's not possible. I think that's cool. All right, so here's some examples that would help us understand that particles are moving. I'm going to give you a couple more examples here in a little bit.
What's the cherry drink?
It's just like Kool-Aid.
What's the cooler?
Iced tea.
It's like sugar that flavors water.
Yeah.
Okay.
I should have just said that, but kind of just say it simpler, but didn't make it simpler. So I'm trying to say it quicker without having to explain. Shame on me. If particles weren't moving randomly, we wouldn't be able to do these things. Now, you would say that a lot of times it helps to stir things, right? To help things dissolve. But things dissolve without us stirring it. And the reason why is because particles are what?
Moving.
Randomly moving with chaotic fast motion. Now, what's moving faster, a solid or a gas? Anyone know?
Yeah.
Gas is moving faster. We'll talk about that as we progress through, but gas has more energy. Everybody got this? Carly?
Yeah.
I'm not going to elaborate on this too much. So here is an example. I'm just going to show you this in a little bit. So I'm not going to, don't put this in. So let me show you this. You've probably seen it. No crazy new earth-shattering thing. But if I put food coloring in here,
Beautiful.
if particles didn't move, would that be able to diffuse throughout the whole glass? By the end of class, I bet you that'll be just all red. But right now, you see it slowly moving?
It's because gravity's moving down.
Well, but it's moving not just down, it's moving sideways too. It wouldn't be able to do that if the water wasn't moving. Okay, and when this heats up, I'll show you this. And we'll notice the difference. We'll come back to that. Over time, don't just stare at that. Oh, that's so cool. Watercoloring in water. Food coloring. Okay.
This mixing that is the result of particle motion has a name, and its name is diffusion. It's why when Mrs. Safford rips a big one, you can smell it. What's that? What's rips a big one?
Yeah.
Methane out of your booty.
What?
When you fart.
Oh. It's for the hard to skin.
It's why you can smell food from the other room. It's why you drive down the highway, all of a sudden you smell this skunk, or, you know, when we were driving back from Breakaway, how many times we smelled the hog farms?
All of that smells real bad. Like really bad.
You don't have any of that in China, do you?
No, not in the city.
Yeah,
Well, in the city you get dumpsters.
sure. But you don't have like hog farmers,
No,
like pig farmers.
not in the city.
What's that that you were in the city?
Since
Oh
Robert
wow,
Brown.
we are not going very fast.
What? Who's Robert Brown?
I will tell you in a second.
Okay. Is he dead?
Mm-hmm.
Cool. I'm not cool, but okay.
Is he dead?
This is a lot of great scientists that did a lot of things.
Yep, but they're still dead. Entropy, that'll get you eventually. All right, you've heard the word diffusion, I'm assuming, before.
Yes.
Mr. Finch.
Mr. Finch, he's the one that's a famous like Febreze.
Yes.
Story.
He gets like the spray bottle and sprays it on all of them.
I'm not gonna do that, okay? That's just, the reason why diffusion happens is because particles can move, right? They're rapidly, randomly moving. Okay, that process is called diffusion. So Robert Brown was the first to notice that particles moved, and this is actually quite interesting how he did this. He basically looked at the surface of water, right? The surface of water, even right now, doesn't even appear to be moving, right? But when he took a microscope and he looked at the surface of water, he noticed that there were like dust particles sitting on the surface of water, right? It would make sense, dust is in the air, eventually settles on the water, right? And he noticed those dust particles were like jolting about and vibrating and moving all over the place. What did that suggest?
Robert Brown is very bored.
That the water particles were moving. And because of it, so was the dust particles on top of it. Which is not like the craziest finding in the world, but I mean, having not known that water moves at a subatomic level, that would be crazy. Alright, we're going to spend the rest of the time talking about the atom. I'm hoping this will be a review, but I'm not going to assume it's completely a review for everybody, especially if you went to a public school last year.
36 particles of matter.
It's our most fundamental building particle. Very important, whoopsies. Made up of protons, neutrons, and electrons.
Learned this in 6th grade.
Good. Good. We're just going to review that quickly. The Americans are like, oh, no, no, no. When did you guys learn this?
Last year.
Really?
Well, we reviewed it.
I have no clue when I first learned it.
Yeah,
It was
me
sometime.
Yeah, we're not going to spend a ton of time on it, but believe it or not, I come across a lot of students who don't know what an atom is, what makes up an atom, where the things are in an atom, and you name it. So we're going to spend some time, you know, we only got like 8 more minutes, so I'm not going to take any more time than that. Okay, so we're going to do like a little box. We're going to go, we got a particle, put this in your notes somewhere. We're going to make like a little like grid, a little table. Particle, charge, location. And we need to have 3 by 3 table.
Okay,
Oh,
so.
I know what you're gonna do.
Yeah.
You're gonna say proton, neutrons, and electron are the negative or positive, and where do they locate in the atom?
Yep.
Yes. Feel like
Yeah,
this
and
guy.
again, most of you guys could probably fill this out on your own, but in case, we need a little quick refresher, we'll do that. We've already identified that an atom is made up of what three particles?
Those three particles.
These ones, protons, neutrons, electrons. I can never spell, I don't even know if I spelled neutrons right. You'd think after 6 years, I guess it's my 6th year of teaching, I'd be able to spell this. I know, right? You feel like it should be something you should be able to spell easily, but sometimes I make mistakes, and I can't spell. You guys know. Okay? I don't want to go too fast, but we are going to continue on and fill this chart out. I guess that's up to you. If you feel like you got it, then no. If you feel like you need a little bit more, just so that it's written in word form when you're reading through in your notes.
Actually, the electrons is outside of protons and neutrons and orbits around it, right?
Sorry, I wasn't listening.
Cool. Okay.
I'm not trying to say to value what you had to say. I was just focused on this.
What's that?
A model.
It's a model of which
Model of an atom. I'll explain it.
I do not know which element that is.
What is minus? Is it?
Hmm? No, what'd you say, proton or electron? Proton's positive. That's beryllium, beryllium.
But how does the rings go again? There's 3, first one equals 3, the second one, how much more? 8?
You're saying the first one goes 2, then it goes
Oh.
8, then it goes 8. Then it
That's
goes 16.
incorrect.
Oh, yeah.
Ha! I like correct.
I didn't look at it that closely.